Yes, very good afternoon. Uh, Hopefully 13 students have been joined. Okay, let us begin with the. We have already done half part of the chapter 5, and which is image restoration and the reconstruction. And today we will do the recovering filters. And before proceeding further, let's review what we have done yesterday, and this is a brief overview about it. And yes, previously we have done image restoration part, and we have also covered on what cases we are using the image enhancement and where we can use the restoration techniques. And it is very simple. In a image enhancements are generally used to enhance the contrast or brightness, or there is a desirable details that exist within that particular image. And in the case of the restoration, in a restoration techniques, we are highlighting the or enhancing the details within the within the image. But the uh, add-on uh, add-on thing in the restorations, we are doing in some kind of a predefined sense. So basically, what we are doing, we are trying to recover the actual image, not the some hidden part of hidden part exists within that particular image. And the restoration is simply a recover an image that has been degraded by some prior knowledge of the degradation phenomena. And what are those degradation phenomena? And the degradation phenomena is basically added with the additive noise. And we already have done various noise model yesterday. And what are those noise models are? And there is uh, there is based on their histogram. Look like that. There is the first one is we have done Gaussian. We have done Rayleigh. This is a mathematical expression for Gaussian and its output shape. And this is a Rayleigh. And then we have done gamma, and then there is a exponential noise is there, uniform noise is there, and the last one is a salt and pepper noise. So the here we can just recognize that how the histogram of all these noise models are look like. And here you can just compare between the Gaussian, this one is for Gaussian, Rayleigh, and Erlangen or gamma. And you can just go through it. And the next one is belongs to the this one is the exponential, because the exponential shape of a histogram. And this one is a uniform, because it's look like a uniform. And the last one is a salt and pepper. And hopefully you all are aware of how to recognize the histogram. That is one of the most important part of the digital image processing. And next we have done restoration in the presence of noise only. So how we can do it? We can do it with the help of spatial filtering. And yes, the simple phenomena is that yes, this is a degraded function. This is in spatial domain, and this one is in frequency domain. And the phenomena is that we can recover that. Okay, yes. We can, this is the original image. We can recover the original image by simply minus the degraded image with the noise model. Now the problem is in the restoration process in a digital image processing is that we can't estimate this particular noise model. Basically, in the initial stage, we are defining some type of a noise models, and we have to recover the image by applying those noise models. But the point is that it is very challenging job to identify this noise. Basically, once the image has been degraded, so there is a in a exceptional cases we can do the same, but this is not a specific method. Now the spatial filtering, yes, the spatial filtering is actually doing all type of performing the restoration of an image, and the spatial domain is the method of choice for estimating and in the situations where only additive random noise is present, and the spatial, and we already have done various spatial filtering techniques in the chapter 3. And uh, okay, before we go towards the spatial filtering, let us understand first what is a spatial filtering and how is it is working, so that you can recognize that uh, the further steps involved in the uh, uh, reconstruction procedures. And just wait for a second. I will just change my slide. Uh, there is a, yeah. Uh, just hold for a second. Yeah. Hopefully, my screen is visible to you, in which it is showing that how the spatial filtering is working now. Okay, I have to check it. Yes. Uh, yes, the screen is visible to you. And let us begin with this point. There is a very interesting, and you must have to uh, aware of that, how the spatial filter works. And this is a we have already done some concepts. The this type of a window or a mask filter, or we can say it as a kernel window. And these are the kernel coefficients, that is W, and these are the various solutions, and this is the actual value. Now, we have to do in a some kind of in a practical sense, so that we can understand that how it is working. Now, the concept is that, for example, this is an input image, and uh, this is a input window. So, in that particular input window, there are 9 pixels are existing, and those are 9 pixels are there. Please note that this is a input image, and this is a input window, which is highlighted over here, and it is divided into just into 3 different parts. And the intensity level of all these windows, there is live from the 224, that is basically that is a 8-bit image, and whose range is lie in between, there is 0 to 255. So 255 means 255 for white, and 0 for the black dark one. Now, yeah, here you can just, I have to split it into the 9 parts, 3 by 3. There is 3 rows and 3 columns, and yes. Now you have to understand what is the X. There is an X which needs to be replaced. So we are looking the value of this X. This is a old window, and this is a old value of that exists within that input image, and we have to identify that X, and we are identifying this X with the help of a 3 by 3 window. So what is that 3 by 3 window? Whose locations are this one is the X. This is the position of our X. There is 0 0, and this is the coordinates, that is 0 -1 on a left hand side at the center, and this one is the right hand side in the center, and this is the diagonal position. These four are the diagonal positions of the window with respect to the this value. So in order to identify the value of a x, which may be degraded by some kind of a noise model, then we can do it with the help of this concept. And then this is what we are doing. We are just multiplying there is a value, intensity value with that kernel window, and we are adding again. We are adding all the pixels from this point to this point, and after whatever we have got as an average, we will update the value of x. And here you can just recognize that and how the values are changing. And here you can just this is an example of a high pass filter, and this is the input image, and this is a highlighted window in which 3 by 3 pixels are there. And this one is a high pass filter, in which there is all the values have been considered to assign the value of this x. So there is a x. In order to find the value of this x, we need to we need to perform some kind of operation, and we are doing the multiplication in a geometric model that we will discuss in the upcoming slides. But yes, in order to identify the value of this particular pixel, we have to multiply uh, uh, we have to consider the entire window. And what is that entire window? This is basically nothing but this is the x. There is a position of an x, and these are the nearby pixels. So you can increase that particular window. You can also consider as a 6 by 6, so that the 6 rows, sorry, by default, you can consider only 3 by 3, and 9 by 9 you can consider it. And this is a format what you can follow while doing the. There is definitely be a odd one, so that your relevant pixel must be at the center. So in case of a 6 by 6, there is no any possibility your pixel lie within exactly within the center of that particular window. So in another case, they have used low pass filter, and the entire the concept is very similar. Uh, the concept is very similar, and here you can just check it out that this is the x value. We have to, and this is a divided into, this is basically built into 3.3, 3 by 3. And in order to identify that particular value, we are considering this, all the values, and once we, whatever we have got after the multiplying on average or by applying the different operations, we will get the value at this particular point. This is a final result. So this is an entire concept in spatial filtering. How we are doing this, and uh, we will uh, understand this concept with the help of some practical implementations, and which we will do in a laboratory. Let's see when your labs will be conducted for this subject, and so that you can able to understand it. So now I am shifting back to the restoration and the degradation process, so that we can continue. Just hold for a second. Hello. Hopefully my voice is clear to you. Now, now back towards the arithmetic mean filter, and which is used for the restore an image. And the arithmetic mean filter, that is definitely there are a lot of filters are there. And first we are just learn about the what are the main filters and what are their different types. So the first type is a arithmetic mean filter, and this is one of the simplest of the mean filters. And this is a expression, and we are just doing the value of a restored image. The value of a restored image at the point xy is the arithmetic mean computed using the pixel in the regions defined by the this sx. And what is that sx? That is nothing but in just a set of coordinates in a rectangular subimage. And in a previous another presentation we have recently done, there is a window is there, and in which we are looking for the value of x, and to identify the value of x we have to multiply with the 3 by 3 window or a specific or any other mask. So they have just written here there is a rectangular window, and the size you can define according to the requirement. And definitely, as the mask is the size of the mask is increasing, you will get the more accurate results. But yes, on the other hand, it will increase the time of computing. So this is a overall concept of filtering. Once you got the point of a spatial filtering, then you can understand it very easily. And this is a value. This is a crafted image area, and we are doing the arithmetic. We are calculating the arithmetic mean. So next is a geometric. In a geometric, what we are doing? We are doing the product of all the pixels in the subimage. So this one is an important point, and we are doing the product of all the pixels in a there is a kernel window what we have considered. And yes, with the help of these filters we are able to get the smoothing results, and we will see the results in our upcoming slide. And here you can just this one is an X-ray image of PCB or a circuit board, and it is the Gaussian noise uh, is added to the to this particular image. So this is a degraded image. Please note that this one is a degraded image in which the Gaussian noise is added. Now, this one is a result of a arithmetic filter, and this is a result of a geometric filter. And in this case, in arithmetic, we are computing the mean, and in this case, we are computing the product of all the pixels within that particular image. Now, you can just judge with your eyes which one is a more clear uh, uh, after the filtering with respect to this particular input image. And you can compare it, and according to me, both are equal with respect to the input image. And uh, in this case, we can't judge with our eyes, but yes, you can recognize that there is a difference between degraded image and a filtered image. There is a very there is a light difference is representing in that particular figure. And now the another one is a harmonic mean filter. How harmonic mean filtering operation is achieved by this expression. And please note that the harmonic mean, this is one of the most important point. It works on a salt noise, but definitely it will not work on a paper noise. So the paper noise is particularly concerned with the dark pixels within that particular image, and this is the brightest pixel. And yes, it does well also with other types of the noise like the Gaussian. So you have to consider it. And this is a contra harmonic mean filter, and uh, which is given by these expressions. And definitely the contra harmonic mean is well suited for the reducing the or eliminating the effects of the salt and paper noise. So please note that this line, what is the difference between the harmonic and the contraharmonic, and what is the advantage of a contraharmonic as compared to the harmonic. So that is directly linked with the salt and paper noise. So this is these are the results, and this one is a paper noise. Yeah, this image is corrupted by a paper noise with the probability of 0.1, and this is corrupted by a salt noise, where you can easily recognize that when we are talking about the paper noise is basically concerned with the dark pixels. The dark some dark values are here, you can observe very easily. There are some dark values have been introduced in the figure, and in this case there are it is not recognized from the this sample, but yes, it can be recognized from this sample. There are white uh, pixels has been introduced when we are comparing this region. Here you can see that the difference between these two, paper noise and the salt noise. In a salt, the white pixels are there, but in case of paper noise, there is some dark pixels are there. So the figure C is representing the filtering results of a contra harmonic filter, and with the different some Q value of quality factor of 1.5 and minus 1.5. And here you can just see the comparison. If the paper noise is there, then it can be recovered as this. If the salt noise is there, then it can be recovered as like this. So this one is a actual figure. This is a previous. I am showing the previous slide, and this is the output image. You can compare these two images with the actual input, and these two are the degraded figures. Please note that, and these are the recovered figures with the help of these two. And similar, there are another type of filters are also there. There is a order statics filters, uh, and in this case, there is a kind of a median filter is there, max and min filter is there. So the median filter is the best known order statistic filter, and it is known as a median filter. And yes, as its name implies that it replaces the value of a pixel. It replaces the value of a pixel by median of the intensity levels in the predefined neighborhood of that pixel. And please note that here if we are talking about the predefined neighborhood of that pixels, then we are talking about the mask. That is a window that is kind of a 3 by 3 or 9 by 9, whatever you want to be considered. And these are the results. And there is a first figure in which that is corrupted by the salt and paper noise. And the another one is there is a result of a median filter of a size of a 3 by 3, because we have used a 3 by 3 mask. And there is a result processing some other results with respect to that particular uh, model. So the another one is a max and min. In max and min, there is related with again median, and the expression of that particular max and min filters. And this is as shown in this particular blocks, and it is used for the finding the brightest points in an image. And yes, because the paper noise has a very low values, it is reduced by the filter as a result of the maximum selection process in the sub area. So these are the some other types of filters are there, and these are the output results. And here you can just recognize that uh, which one is good and which one is not. So again, please note that it is not mandatory that the results of the next filter will always better for you, and because it entirely depends on the input image, type of the input image, and the degradation phenomena. So there is a midpoint. You can please go through this point. There is a midpoint between the max and mean value. Uh, there is area specified by that particular filter. Now What is a periodic noise? Periodic noise, yes, you all are familiar with that. What is the difference between periodic and the non-periodic signal? And the periodic noise can be analyzed and filtered quite effectively using the frequency domain techniques. Frequency domain techniques, and the basic idea is that the periodic noise appear as a concentrated burst of energy in the Fourier transformation and at the location corresponding to the frequency of the periodic interference. And this approach is to use a selective filter to isolate the noise. And what are those type of filters? That is, we have already done band pass, band reject, and the notch filter. And that has already been discussed in chapter 4. And there is no difference. Yes, uh, there is no difference between how these features were used in a frequency domain. That is chapter 4, which is belongs to the frequency domain, and they the way they are used for the image exploration. So both are using in the same way and as in a frequency domain and in a restoration process. So that is one of the most important topic in restoration. We can restore the image with the help of inverse filtering, and this is the one of the simplest approach. If we are talking about what is the simplest approach in a image restoration process, definitely the inverse filtering. And in this, we can compute an estimate. We can compute an estimate of an recovered image of the transform of the which is a transform of the output image by simply dividing the transform of the degraded image. And here you can just go through this expression, and it can also be represented in form of this. And you can please note this point. Even if we know the degradation function, and what is that degradation function? That is, we are talking about this. This is a noise and degradation functions. So please note that there is a very small values, and it can also be like 0. So it is very there is a one point, and another point is that the NUV is a random function whose Fourier transform is not known. So that is another problem in the inverse filtering. And if the degradation function is 0, HUV is 0, and or you can entirely consider it as a 0, then it dominates the estimated recovered image. So please note that there is no provision of a handling noise. There is no provision of a handling noise in the inverse filtering. And in order to solve that particular problem, we can use the minimum mean square error. That is, please note that that is a different kind of a filtering, and which has been designed to overcome the problem of inverse filtering. In inverse filtering, there is no provision for handling noise, and the minimum mean square error we can we can use this approach that incorporate both degradation functions and the statistical characteristics of the noise into the restoration process. So the method is found in considering the images and noise and the random variables, and the objective again is to find the estimated recovered image of an uncorrupted image, that is called as a F, and such as a mean square error. There is a difference between there is an actual image and this is an estimated image, and here we are just identifying the error mean square. There is a mean square error between them, and how it can be minimized. That is defined by this operation, and where E is a expected value of the argument. Please note that there are some assumptions with respect to this model. There is an image and noise is uncorrelated, and one and other has zero mean. Gray levels in the estimated are the linear function of levels in the degraded image. So these are the assumptions while you are implementing this minimum mean square error filtering, and this is a operation you can just compare with respect to this one. Here you can just compare it, and then uh, yeah, that is the degradation functions have been modified, and in this minimum mean square error filtering, and these are the some values which is uh, defining all these terms which is used in that particular filtering, and this is some uh, outputs related to the uh, now we will do with the one by one. That is a 8-bit image corrupted by the blur and additive noise, and this is a result of inverse filtering. This is a result of inverse filtering, and here you can recognize that this is a result of a winner filtering, or we can say it as a there is a minimum mean square error filtering. So you can just check it out. The what is the difference between those inverse and the minimum mean square? So the both are given to you. Just this one is considered as an input image, and this is with the uh, changing in magnitude. These are three examples, and this is the three results. These three results are the of inverse filtering, and these three results are the of the minimum mean square error. So here you can see that how much it is better as compared to the inverse filtering. So this is a entire concept of a restoration process. Yeah, okay. Okay, this is the entire concept of image restoration and the image degradation and the restoration. And hopefully you will, once you have read the entire chapter, then you can understand that what are those terms and why we are doing this. And we will, in future, we will also do some kind of experiments with the help of inverse filtering and the window filtering, so that you can learn about the how it works with respect to the different input figures. Now, please, it's a time to mark your attendance, and yes, if you have any problem in restoration and image restoration and the degradation process, then you can please feel free to ask, or uh, till then you can mark your attendance. Links have been already been posted in the chat box. Once you have marked your attendance, please confirm me, and then you can leave the session. And tomorrow is your discussion session, so be prepared with some questions relevant till fifth chapter. And you can go through. You can also go through the all the PPTs which have been uploaded on Google Classroom. And yes, if you have any question, then you can please feel free to ask. Otherwise, you can mark your attendance and leave the session.